Hello, welcome to video 40 in the lecture Advanced Mathematic Modeling. In the last videos I spoke a lot about the properties of power law distributions and inequalities and what this has to do with economy and so on, for example. But one practical issue I didn't discuss yet: what do you do if you have a sample of data and you want to know is this a power law or not, or maybe more weaker question, you just want to know what's the an estimate of the critical exponent. And I want to discuss this now in this video. Okay, so like of course, like when you want to estimate a distribution, we have seen how to do it. We can make a histogram. To estimate the distribution, probability density function, and that's now a bit repetition what we had before, when people just make a histogram of the x values. Let's say x is the random variable again, and if you just make a histogram with normal values of x and you plot then your histogram, then you have the problem that you know that in a power law that you have this arbitrary large values of x, but not so many of them, so the histogram will be very sparse for large x, and for small x you will have a lot of entries. So typically such a histogram, so you will get a lot of entries here and not so many for large x. And now, of course, we want to plot it in a double logarithmic scale. So let's write here log. Oh, sorry, it's maybe I write it like this so that you can see it better. We want to plot log of the histogram versus logarithm of x, and then so typically then you would like to see here a straight line if we have a if our data is really coming from power law distribution, a perfect power law, and then there will be here think a bit. Yeah, I mean, I've always to think like, how does a log transform work? So like if you would make a histogram with equally spaced bins and then you make a log transform, then you will have for small x you will have large distances in the bins, and then the distances in the bins get smaller and smaller and smaller and smaller, squeezed together. And now when you make the histogram, then here you have for small x you have large bin sizes, so you have a lot of data, and you get so you see here the nice if the data really comes from a power law, you see data points which lie on the line, but then the bins get smaller and smaller, so you don't have enough data in the bins, so you start to see deviations. And when we connect this line, then suddenly we start to see some fluctuations. And then the bins get so small that sometimes you have misses, you don't have data, you have here don't data at all, and it fluctuates a lot. Yeah. So that's typically if you have a power law and you make a histogram with non-log bins and then you plot it on a double logarithmic plot, then it looks like this. And now you see this data, this histogram, and now you think, can we now put here a scaling line through and see, does this really follow our power law distribution? And the problem is always you want to know what's in the tail for very large x, but exactly in the tail, and where you're interested in to see what are the properties of this very large random events that very large x values, you don't see so much because you have the strong fluctuations. So still in the literature, from occasionally we see this kind of histogram, and so then it means it just was poorly done. So what people should have done, they should have made bins which are logarithmically spaced. So now if we now make a histogram and have here log x, and here we have log of our histogram, and so if the bins are really equally spaced here on a logarithmic scale, and then you have points where in every bin you have enough data points, and now you can try to fit a straight line through the whole thing, and then you can see if this is make a straight line fit and see if this data is a power law. So the first thing is you need for histogram equally spaced bins on a log scale. So that's maybe the first thing to do. Or, I mean, so like, but the question is, how do you get equally spaced log bins? That can be problematic because, like, let's say x is discrete value. So like x is only a discrete distribution, so you have only 1, 2, 3, 4 and so on. Then you can start here, the first bin goes from 0 to 1, the next then from 1 to 2, the next from 2 to 4, and the next from 4 to 8. So you can make this binning, but you don't have much freedom to do this, to do the binning. And then, but then we also learned a trick. So what you can do, you can make a alternatively, or so we can make a log transform. And say y is just the logarithm of x. Then we can make the histogram of y. Yeah? And then we just need to make the variable transform backwards. And then you make a plot of maybe I do this here. So we make a plot. Now we take the histogram of y. So we look for the histogram of y. So we and then we need here, because we have a log scale, log of the histogram of y, and then we need to subtract y again, and this comes because we want here to plot the histogram of our variable x, so the log of histogram x, and if we plot the log of the histogram of y, of the log transform, minus y, so this takes care of the variable transform, and this we plot against y, and so that's a logarithmic scale because y is log x. Yeah? And when you do it like this, then you can now, so from this variable y, which is log transform, you can now take your normal histogram algorithm, and then automatically, if the histogram uses equally spaced bins, then y is equally spaced. And then maybe your data points are something like this. And now you can try to put here a straight line for the whole thing. Yeah. So that's the first. Take either equally spaced log bins on a log scale, or make a histogram of log transformed values. But then you have to take care that you transform back in order to plot really the histogram of the original values. Now the next thing is, even though that's very important, many people recommend not to rely too much on this. So, but there's still problems. Yeah. And this has to do with the fact that essentially, I mean, we're speaking here in such a plot about very, very different scales here. And if you know to make here a straight line fit through this, the question is of the value you obtain by a straight line fit, does this really give you the slope of your power law? I mean, if this should x2 minus alpha. So what has the slope of the red line to do with alpha, and is this a good estimator? And so of course you can explore this, you can generate artificial data which are taken from a power law distribution and make this procedure, and then look how good is the estimate from this straight line fit. And if you do this, this shows this is actually not so good. We need something better, and I will show you later in this video how we can do it a bit better. The other thing is, very often the power law holds only for a certain range. Yeah? So what do you do? So the first thing is, so we make here the slope. Let's call this alpha bar, and then the question is alpha bar a good estimator of the real critical exponent alpha? Yeah. So there are still problems, and that's typically not always the case. So maybe I should have written this here. Is the slope of a regression line good estimator? Yeah. And but at least, and that's from my experience, it's not the best estimator of the critical exponent, but it's in the right ballpark. So I mean, if you do this and you find here a straight line and you get an alpha that you estimate from the slope, it's at least in the neighborhood of the real alpha. But then the thing is, like, you would always find a straight line on a double logarithmic scale if you don't have many orders of magnitude. Yeah? So the thing is, you can trust this only if x varies over, and here I would say you should have at least 2 orders of magnitude. So this means, like, for example, your values go from 1 to 100 or something. Then you have 2 orders of magnitude, and if you see it's a straight line for 2 orders of magnitude, then like in practice you could say, okay, that's pretty much a power law. Yeah, I mean, of course, if you have 3 or 4 orders of magnitudes, it's much better. But frequently we have sparse data and we have just 1 order of magnitude, and I've seen people doing a log scale when there's only half order of magnitude, and that's, frankly, that's bullshit. I mean, it doesn't tell you anything. Yeah, in order to see if it's a power law, you need to vary some orders of magnitude. So that's important. I would say 2 orders of magnitude, then yeah, okay. And then the next thing is, I mean, so the power law is always only valid typically in a certain range. Yeah, because like a true power law would mean that you have arbitrary large x values, and in practice you never have arbitrary large values. So this means, so you have, so what's the width of the scaling, the range of the scaling regime? So what do we mean by this? So let's assume again, here we have our log plot, log x. Here we have our log of our histogram. Assume we do the binning correct and so on. But then the question, sometimes you have something like this here, you have maybe something different. For example, we could have something like this. So we have a certain range where we have a straight line, but then we have a transition, and then we have something else. So kind of a cut-off for very large x values. Yeah. So now the question is if your data in your histogram look like this, and suddenly you see curvature. And here I made this very strong that you can clearly see it, but this curvature might be very small. So now you have different options. So you could either say, okay, I try to find a straight line fit through the data. It will go like this. But here, I mean, when I exaggerate this, you will see that's maybe a bad fit. Then maybe better fit would be to say, okay, here is maybe scaling regime, so we fit a power law through this. And maybe we have another scaling regime, and here for large x maybe we have a different power law. So maybe we have transitions. Or maybe we could say here we have a power law, and then we have here an exponential cutoff if this is still curved. But then the question is, and that's typically the case, so that you have a power law over the whole range of your data is rare. Typically the power law holds only in a certain range. How do you find this range of the scaling regime? So we say that's the scaling regime, the regime where the power law holds true. And here my trick is, we in order to see this, we take local regressions. So what do I mean by this? So here we plot again our log x. And now you make local regressions to the data, to the histogram. And now the question is, what is local? So you need to have a parameter, a certain width. Maybe I say take 3 points, and then I make a straight line through the first 3 points. And from this I get a slope, and here I have a small slope. So maybe the slope was small. And here I plot the local slope. Then we make a regression, maybe here through these 3 points. Here, regression line, and we have a slope which is of the same order. So, because like here the data always follows power law, so the local slope is the same. If you want to go to the edge, you have only 2 points, then maybe you make the local slope only to the first 2 points, and then you would still see here something like this. So we see here the local slope is constant. And now we approach this value here, and now if you make a local slope for this point here, we see the local slope is a bit larger. So local regression through these 3 points, and suddenly we see, oh, here we go a bit higher. And then we make a local slope through these 3 points, and suddenly we're here at this point, and then it doesn't change anymore. Here. Then we would see in the local slope we have here a range where the local slope is constant, and then we see transition, and the local slope is increasing. And this could, if you have something like this, then you could say, okay, here we have a superposition of 2 power laws. For small x we have a power law with a small exponent, and for large x we have a power law with a high exponent. So because like this you can now better see, you just look for plateaus in here. Yeah? And so a scaling regime means you need a region of x values which have more or less the same local slope. Yeah? And that's in practice the method I use always when I have such data. I look at the local slopes and see if I find scaling regimes, and if I find something like this, then that's typically an indication that I have really a power law here. Another thing is, sometimes, I mean, you know, if you have a power law, then also the cumulative distribution p larger of x should also be a power law. The cumulative distribution p larger of x should also be a power law. Yeah? And so many people recommend that you not only make a log-log plot of your histogram, but you should also calculate the cumulative distribution. And this you could calculate very independently, but with the rank plot. I mean, we have seen how to do this. You make a rank plot, invert the axis, then you have the cumulative distribution. And now you plot this on a double logarithmic plot. On a log-log scale. And see if you still have a straight line. And very often the cumulative distribution is more sensitive, and we will see this also later why this might be the case. And so if also the cumulative distribution also follows a straight line, yeah, and you can make this local slope analysis also for the cumulative distribution on a log-log scale, yeah, then you're again more sure that you're dealing maybe with a real power law. Yeah? And why do I show you all here this potential problems here? The thing is, like, because it's known now that in the literature we have a lot of fake results where people made a too naive histogram of such data and too easily just from the regression line took a certain value a slope, and then they claimed that this data follows a power law with a certain exponent, and later it turned out if they would have done the analysis a bit more rigorous, the data was different. Yeah? And so, but if you follow these rules of thumb, so first you take care that the data is equally spaced on a log scale. You take care how to estimate the exponent. I will show you something better later. You take care that your values vary over at least 2 orders of magnitude. You look here at the local slope to see where are the scaling regimes, and so the data should vary over 2 orders of magnitude in the scaling regime here. Yeah, over 2 orders of magnitude in the scaling regime. So if you find here such a range here where you could say, okay, here we have a slope which is more or less constant, and this here, that's the scaling regime. And in this regime the data should vary over 2 orders of magnitude, not in the whole thing, because like if in the whole thing you have 2 orders of magnitude but you find a straight line only in a small range, so you have only small range, yeah. But if this is 2 orders of magnitude, yeah, then I would say, okay, let's trust this is a power law, yeah. And then fourth, you should look also in the cumulative distribution and look how does this look on a log-log scale. Is it also following a power law? And then the slope in the cumulative distribution, of course, should differ by 1 from the slope of the normal histogram. And if you use your accumulate evidence, then you might have a real power law. Now, there's some kind of nearly religious or philosophical debates in the literature for some data sets if this is a real power law or not. Because like people are really fascinated. Like if you have a power law, a true power law, this has also a lot of implications because there's only so and so many processes which generate a power law, and there can be debates, but for practical purposes I would say it doesn't really matter so much. I mean, if you make such a histogram on a double logarithmic scale and you find something which looks like a straight line, maybe it differs a little bit but not so much as here, yeah, at least you have a long tail in your data. And many things I showed you before with inequality and all these things apply also for any distribution which has a long tail. Then it might not be a real power law. There's other distributions which also look a little bit like a straight line but are not perfect power laws because they deviate a little bit. There is some intrinsic curvature here. But then you could say, who cares, my data has a long tail and it has all these problems associated, or the properties associated to these distributions here. And sometimes, so it's maybe a fake discussion you see in the literature when people really want to know, is it a true power law or not? And then you try to estimate this, and you have all these problems associated to this. Okay, so that's so my approach to analyze power law and data, to take care of these rules, and you're kind of on the safe side. But in order to estimate the slope here, there is something better than taking the straight line, and this I will show you. Okay, I should make it in the next video because this video is already getting too long. So I will show you how to estimate the slope with the log likelihood method, but I do this in the next video. For the moment, thank you.